In this video, we are going to study how we can give the stability for the upstream as well as for the downstream slope of a earthen dam. Basically, we had studied that because of the various failures which are occurred on the upstream as well as downstream as well as in the body as well as in the foundation. So during the construction, after the construction, we need to give a special inspection and maintenance to the given earthen dam. So here are some analysis that by referring that or by giving that analysis for the certain slope, we could save and we could protect our earthen dam embankment from the failure. So here are the four sections: the stability of a downstream slope during steady seepage, stability of an upstream slope during sudden drawdown, stability of an upstream and downstream slope during and immediately after the construction, and the stability of a foundation against the shear. So basically, we have to give the slope analysis of slope stability as well as here we are giving the stability for the foundation as well as we are giving the stability for both the slope of a given earthen dam. So because of the various conditions that slope might be failed, so to protect from such a condition, we need to give such a type of a stability analysis. But before giving or before choosing the slope stability, here one of the scientists, the Swedish, he had been gave us the one theory, one method to finding out the slope stability. So by using that equation, by referring that method, we can apply this slope stability for the downstream as well as for the upstream as well as in the foundation to protect it against the shear. So let's start or let's study the Swedish circle method, which is very important, and in the university question paper this question will be asked you for the 10 marks. So here the Swedish circle method of a slope stability. See, out of the numerous methods of slope stability which have been derived over the last 40 years, the Swedish slip circle method of stability analysis is one of the most generally accepted methods. What exactly happened in this? What exactly had done in this method? See, in this method, the potential failure surface is assumed to be a cylindrical, and the factor of safety against the sliding, which is defined as the ratio of average shearing strength, which is determined by a Coulomb's equation, which is denoted as a H is equal to C plus delta tan phi, to the average shearing stress, which is determined by the statics on the potential sliding surfaces. So here in this method, basically we are referring and we are taking as a consideration as the potential failure surface is assumed to be a cylindrical one, and this factor of safety against the sliding should be taken into consideration, which is determined or which is defined as the ratio of a shear strength, shearing strength, average shearing strength, which is finding out by using the Coulomb's equation to the average shearing stress, which can be determined by the statics on the potential sliding surface. So in order to find or in order to test the stability of this slope, a trial slip circle is drawn. So and the soil material above assumed slip surface is assumed or is divided into a convenient number of vertical strips or slices. So here I will show you how we can decide and how we can assume the slope surface as a cylindrical one. See, if we are assuming that that upstream slope that we are going to consider, let's consider this. We are going to consider the upstream slope. So this is our upstream face, and here according to this we are considering that here or by assumption this sleep circle will be look like a cylindrical one. It is assumed that. So here the trial sleep circle method is, or trial sleep circle is drawn here, and the soil material which is above the assumed sleep surface is divided into a convenient number of vertical slices. So here from this point, if this is a B point and if this is the C point, this is your hill point of the C section, earthen dam section. So in this section, above this sleep circle, you can divide this section into a convenient number depending upon the length and depending upon the slope of a upstream section. So here right now we will get certainly slice 1, slice 2, slice 3, slice 4, slice 5. So here we will get the 5 slices here. See, because of the small area is there, but according to your upstream slope and according to your that length of the upstream side, you can divide it into equal distances or at equal slices. So when you divide this, then the forces between the slices, the forces which are generating by these slices are going to be neglected, and each slice is assumed to act independently as a column of a soil of unique thickness and width p. So this slice will be act as a independently, which has the column of a soil of a thickness and a width, unit thickness and width is equal to the b. So when we draw, after drawing this and after considering the forces that we are going to neglect, then the weight of each slice is assumed to act its center. So here basically we need to draw a weight of that particular slices. Means what? Here, if this is your slice 1, if this is your slice 2, if this is 3, if this is 4, this is 5. So for this slice 1, so from this 0 up to 1, if you are drawing a center line here, if from this 1 up to 2, if you are drawing the center line here, 2 to 3, if you got the center line here, 3 to 4, you got the center line here, 4 to 5, you got the center line here, again 5 to 3, you got the center line here. Fine. So according to, and here we are assuming that the weight of each slices will be act as it's a center. So here this is nothing but the weight 1. So for the slice 1, this is weight 1. The second is W2. This is your W3. This is your W4. And likewise for W5, W6. So if you are having 7 slices, then definitely you will get the number of weight of the slices is equal to the 8. Fine. If you are having 5 slices, so basically what you are going to do is you are assuming that this weight of the slices will act at its center only. So if this weight of each slice is resolved, see, this is the upstream slope, this is the inclined part. So here we need to resolve this section into direction. So here for the better calculation, we are resolving this into a horizontal as well as in a vertical direction. So here this weight of the slices will be resolved into a horizontal as well as the normal or the perpendicular direction. So when we resolve this section, this W1 or weight into which is parallel to the upstream slope, then this component is called as a tangential component and which is denoted by a T1. When from this center line, from this W1 line, if the secondly, which is normal components will be drawn, so here this normal component will be denoted by a N1. So here basically weight of each slices is resolved into a normal and tangential component, and then the normal component will pass through the center of rotation. So we have to resolve this normal component like this, that we will get a certain center, or we will get a center of a rotation. So once you get the N1 here also, from this point again parallelly to the upstream section, then here you will get a N2. See, then again here also for this section also you will get a N3. Fine. So all these normal component that you are getting here, so as you are passing further on the downstream side or in the downward direction, this normal components will be shifted or this part will be shifted to the left side, and this normal components then will be act as a or taken as a negative. So here we will get not a normal component but a tangential component that will create the shearing resistance. That tangential components will be taken as a negative. So here after getting all the normal points, when we draw this, when we extend this, extend all the normal components from the each weight of the slice, here definitely we will get the center of the rotation, which is denoted by O, and this distance is nothing as a radius of that rotation part and the radius of that curve. Fine. So after getting all this normal, after placing the normal components, so exactly what happened? See, this normal component does not cause any driving moment on the slice. Only that will be passing through this slice, and that normal components will be passing and we are developing a certain center. So here the tangential component, that T, which is causing or which is responsible for causing the driving moment, means if this driving moment, and because of the friction, because of the that moment, that force that will be acting along with the slip circle, along with the slip surfaces. So here some friction moment and shearing resistance will be occurred on that section. So driving moment will be developed, and because of this driving moment, what exactly happens is driving moment will be calculated. So it will cause the, which is value which gives us a T into radius of that slip circle. So the tangential component of the few slices at the base may cause a resisting moment. See, after this, I said in previous section also, once the normal component shift its place from right to the left, then obviously the tangential component also acts in the reverse direction. So once if the normal component, if the normal component will be here at the left section, so definitely your tangential component will be act in the reverse direction. So this tangential component will be act as and will cause a resisting movement. So some of the tangential components will responsible to cause a driving moment, which can be stretch out the slip surface of that given section, and this resisting moment will definitely protect that slip surface against the driving moment. So suddenly a equilibrium will be balanced, and this moment, this component will be we have that value is equal to T into R. So when the tangential component will be act as a or will cause a resisting moment, definitely here we have to take the value for the tangential moment is equal to minus the because of the reverse direction, here the value becomes negative. So this is the diagram for the certain that Swedish circle method here we are totally based upon, and we are deriving our equation totally on the basis of a trial sleep circle method. So yes, here are the explanation about the same sleep circle surfaces. So you can read here. So the weight of each slice is assumed to act at the center. Its weight of each slice is resolved into a normal and tangential components, and then these normal components will pass through the center of the rotation. Hence, it does not cause any driving moment. The tangential component, then we can find out by using this equation T into R, where the R is the radius of a sleep circle. So for the few slices, the tangential component will be a resisting also. So its its symbol will be a negative one. See, if the C is for this sleep circle, if the C is the unit cohesion, and delta L is the because of this sudden change in the length. So if we have the equation as if C is the unit cohesion, and delta L is the curved length or change in a length of each slices, then here we will get the equation as C into delta L plus tan phi, and phi is nothing but the angle which is made on the specific slope. So for the entire sleep surface, you can see, and if you remember the previous diagram, so for the entire sleep PC, we have a driving moment. MD is equal to the R into summation of T, and resisting moment MR is equal to the RC into summation of a delta L plus tan phi summation of N. So here we will get the resisting moment equation and the driving moment equation also. Then we know that the summation T is nothing but the sum of the here you can see summation T is nothing but the summation of all tangential components. Summation N is the sum of the all normal components, and here summation of a delta L can be find out the curved length of a sleep circle. So it can be find out by using the equation as 2 pi r delta r upon 360, because it's a curve section. So the factor of safety can be find out by using that equation. So here we will get the factor of safety is equal to MR upon MD, resisting moment divided by driving moment. So here finally we will get the equation as this is the factor of this is the delta L value. So here by substituting C into delta L plus tan phi summation of N divided by summation of T. So we can use this equation for finding out the factor of safety against the sliding. So again, in order to find out the normal components and the tangential components, we need to develop a N curve and T curves. We need to draw these curves basically. So by plotting this curve, then we can plot the ordinates which is having a value is equal to N and T for the different strips, and then joining them by a smooth curve like this. If this is the upstream slope and this is the sleep circle, again if we divide this into 1, 2, 3, 4. If we have a 4 strips itself. So here again we know that we have a normal, we have a tangential, and this is our W1. This is N1, and this direction is in the downward direction. So it's a T1, and its direction is here, and its direction is again in the downward direction. Likewise, we got the each strip we got the same. Here you can see, yes, here. So from this point you will get, this is the center point, this is the center. We had already decided that at the center itself the weight of the slip will be acting. So here the W2, here the N2, and here the T2. So again, likewise we will get the equation for the further strips. So here for this each strip we can consider that, and we are here already discussed that this strips has a certain unit thickness and a width. So now by plotting this N curve and T curve, so the area, see, if this is the slip circle that we can develop and we can plot by using the trial slip circle. So after this, if we want to find out the that N value, so again here we have to plot the rectangular plot method. By using that rectangular plot method, we can divide this, we can set a boundary, and we can divide and we can plot the normal components in this, and this area can be measured by using a planimeter, and then the summation of a N, summation of a T can be found out. So likewise we can find out the weight, summation of a weight of each slip circle, that can be found out by using the equation as W, summation W is equal to P into bracket Z1 plus Z2 plus dot 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 1 plus M upon 2 into 7. So this is the one of the equations. By using that equation we can find out the weight of the given slip surfaces. So after finally finding out this, we can put the value in the previous equation and we can find out the factor of safety. The main agenda and main purpose is what, to finding out the factor of safety against the sliding. If this is within the value, and if the factor of safety that should be a safe one, then we can say that this slope is safe against the slope. That slope will be safe against the failure. So here, once we can find out the value of yes, here you can read the points once again. So we are assuming that the width of each slice would be, then total width will be finding out by using this. Here some typing mistake is there, so I had already written down the equation in previous slide. Just check that slide and check the weight formula. So we know that once we finding out the W, so once we get the value of a W, then easily we can find out the normal component at a W into cos alpha, and T can be finding out by W into sin alpha. So we will get the value for the N1, N2, N3 and likewise, and we will get the summation of the even, normal as well as the tangential components. So by referring all these values, we can finding out this N, T and W value. So here are some explanation about this. So the method that will be here, that will be showing in this table, it's W1 here. This is W1. So we will get here N1. Here we will get the T1. Here the W2. So here we will get the N2. Here we will get the T2. N3. I'm sorry, W3. Here N3. Here T3. So likewise we will get, and after that we will get a summation of N here, summation of a T here. Fine. So likewise, this is our third method. First method, rectangular plot method. उसके पहले we had preferred the N curve method, T curve method. Then we are following the rectangular plot method. So rectangular plot method. After this, by using this equation, we can easily find out. First of all, we need to find out the W component. Then after getting the W for each slices, we can find out the N component as well as the tangential component. So in this manner, we can find out the N and T value, and after getting that value, we can easily put this value in the factor of safety against the sliding equation, and we can easily find out the factor of safety. So finally, the how we can locate the center of a critical slip circle. Yes, we know that once we draw the slip circle, because it is totally based on the assumption. So basically here also we need to study a method how we can locate the center of a critical slip circle. So see, in order to reduce the number of trials, because it is totally depend upon the trial slip circle method. So in order to reduce that number of trials to finding out the center of a critical, that means if this is the upstream and here we are drawing the slip circle method, after putting the each slice, this is the center, each slice has a weight, each slice has a normal component. So each normal component, when it pass and when it meets, so certainly at some points when it meets at a certain single point, it coincides but certain point, this will be your center. Previously we had discussed that part. So here also at what part and up to which part we are going to draw this slip circle again and again and again. So in order to reduce these trials, here we are going to find out, and here we are going to locate the center of a critical slip method. So for locating this, we are using the Felinius method. Felinius is one of the scientists who gives us the method of locating the locus on which the probable center may lie. So for this given situation, Felinius gave us a certain method. So see, for the homogeneous soil or for the homogeneous section, the C5, we said that we have a C5 soil. So center of a critical slip circle lies on a line PQ, in which the point Q has its coordinates h downwards from the toe and 4.5 h horizontally away. It means that if we are talking about if this is a homogeneous one, if our earthen embankment is the homogeneous one, so definitely if this is the upstream slope surface, and yes, we have the that height of this is your base, and certainly if from this point we got the top width. So yes, we know this height, we can find out this height. Here is the angle, and when we draw this slip circle, so we will get second angle which can be made with the horizontal and which can be made with the radius of the slip circle, and it is denoted by a alpha. So yes, certainly that value will be reflected and will be located from this hill point again in the downward direction. Here we will get at the h distance, we will get 1 point. And again from this point, if we are plotting this distance as 4.5 into h, so here we will get somewhere its point. So if we are giving the name as x, and here we are giving the name as a q. So if this point will be meet, so here we can pass and we can stretch out this this line in the straight manner, and after stretching out this, yes, so I'm stretching it, so certainly it is slightly disturbed one, but it's a straight line we will get. So after stretching here, So we will know the alpha value and here the beta value can be also be find out, or certainly the slope will be given. So based on this, if we are drawing a certain line which is joined to this section, so here we will get one point which is nothing but a P. So this center of a critical slip circle lies on a line PQ in which the point Q has the ordinate. This point Q has the ordinates, horizontal or coordinates as a 4.5x and vertical as a h. So the other point P obtained with the help of a directional angles. So yes, by using this directional angles, here there is another angle. So we can plot this P point, and if once the P point will be plot, and once the P point will be getting, then we will directly join this two slope and this two line, that is P and Q, and we can say that this P is our center of a slip circle. So when the line PQ is obtained, the trial centers are selected on it. So once we got this, so here we need to select the trial centers. So according to the Fellenius, the center of a critical slip surface is located at the point P for the purely cohesive soil. If the your soil is a purely cohesive, so here your center will be, according to the Fellenius, the center of a critical slip surface is located at here only, P point only, when the purely cohesive soil is there. Means the phi is equal to 0, then we are plotting and we are considering this P as the center of a critical slip surface. And when we have, and for the C5 soil, that means a cohesion-less soil, the center of a critical slip surface lies above this point. Above this point on the line QP produced. So once this line will be gauged or was got, so after getting that point here, for this condition, that is a phi is equal to 0, the purely cohesive, here we will get the P center, and when the phi C5 or cohesion less is equal to 1. So for this we need to plot again the centers above the P point. So the factor of safety corresponding to each center is calculated again for the above when at each section and at each distance whenever we are plotting the center. So for this section we are finding out the factor of safety, and after getting that factor of safety, here we are plotting this as the ordinates on the corresponding. Here we are plotting this factor of safety as ordinates in a vertical manner, or it's parallel to this upstream section, and after plotting this, the smooth curve will be obtained. So here this center of the corresponding and the curve which is having the lowest factor of safety is your critical center of the given slip circle. So in that manner you can find out and you can locate the center of a critical slip. So Fellenius method will be used for locating this slip circle center. So you can read this point. Here are some slopes are given, directional angles are given in the degree. So basically for the upstream section, these angles will be used for locating and for getting that upstream section line. Here you can read this point for the condition cohesive soil, and for the cohesion-less soil, here where exactly the center will be located. You can read this. So according to this, we will get the idea how we can find out the factor of safety and how we can locate the that center of a critical slip circle method. So by using that equation, we can apply and we can use this equation in each condition for the upstream, for the downstream itself, and for finding out the both stability of a downstream as well as upstream. So we are using this, and we can find out this factor of safety, and we can check whether our dam is safe in a given condition and given zone. So certainly in your syllabus, this part up to this part only you have to study. No need to study in detail in the stability analysis or that four section that you are given. So only you have to write down the name, and you have to write down the particular section of that stability analysis. And here you are going to explain only a Swedish circle sleep method. So the question will be asked like this: explain the Swedish circle sleep method and how you can locate the center of a sleep circle method. So all these points you have to write down. You will get a definitely full marks for this question. So thank you for the watching.